right? Neuroscience is a huge field. It spans, very, molecular subcellular processes that happen to occur within neurons or other cells in the nervous system, all the way up to, how does the brain produce behavior? And our program is really focused on that higher level, right? How do we understand the relationship between circuitry in the brain, computations that the brain is performing, and the kinds of behavioral capabilities that those circuits and those computations support, right? And so that's very generally, that's the focus of our program. So we use, modern technologies, high density silicon probes, large scale 2-photon calcium imaging microscopes. So this is, we can use tools from molecular biology to put sensors, fluorescent sensors, into nerve cells. And then every time there's an electrical impulse, because the unit of long range information transmission in the brain is an action potential. It's an all or none electrical impulse, which often popularly is likened to the ones and zeros of a computer, though it's very different. Every time there's one of these all or none electrical impulses, that causes a huge rise in calcium. So that allows us to record the electrical activity from many thousands of neurons simultaneously. Okay. And at the same time, because we're interested in the neural basis of behavior, we have an animal that's behaving, right? When a human being goes in for a deep brain stimulation surgery, okay, that person is awake when you're putting electrodes into their brain because there are no pain receptors, there are no sensory receptors, mechanosensory receptors in the brain. You don't feel it, right? So you can put an electrode into the brain, the animal doesn't feel it, and we can look in on, thousands of cells are doing in the context of a behavior. And it's not just any behavior, we design behaviors, we train animals to perform behaviors that isolate and exaggerate some particular brain function we're interested in understanding. So the third thing in terms of acquisition of data that's very important for us is the acquisition of behavioral data. And this is where techniques in machine learning and artificial intelligence also come, right? So nowadays, computer vision is much more powerful than it was even 10 years ago because of the, advancing performance in deep networks and things like that for image classification and recognition. So we can take high-speed video of model organisms that are performing some behavior and then use markerless tracking to gain kind of quantitative descriptions of animals' behavior and then relate the behavior to the high-dimensional neural activity we're looking at. Since my laboratory is studying a lot of neural circuits that we think implement algorithms like those you find in computational models of reinforcement. And we are going back and forth between building computational models and the data we're seeing in neural activity and the data we're seeing at the level of behavior. No, so, one of the things that's different about the brain as compared to computers is that computers generally operate serially, right? They take some input, they do some processing on it, and they produce an output, right? The brain is a massive parallel computer of varying degrees of depth, right? So you have short circuits that go from sensory input to motor output very quickly, like in the case of reflexes, right? You have medium ones that go somewhat into the brain before coming back out again with relatively simple processing. And then you have very, very deep sensory motor loops, okay? And all of those mechanisms are operating in parallel. And so one of the reasons you might need in a system like that, the ability to both vote for and against certain behaviors, is because if you've got all of these parallel paths for producing behaviors, you need a way to basically suppress some of them potentially, right? So that, the one you want to select actually wins out. And that's not necessarily something that's present in a lot of the control algorithms that are, say, being used to drive a self-driving car or, you know, do any of the other things that we're asking AI to do these days. Yeah, so, you know, AI is entering in a big way, I think, into medicine at various different levels. Being able to take in large amounts of data and use it to predict, you know, outcomes, using it to be able to decide courses of action in terms of treatments and things like that has huge potential. But one of the reasons I think it's important to take a more neuroscience-inspired approach is that, as I said, these algorithms can fail, right? They need a lot of curation still. You need to have human beings, you know, looking over the shoulder of these algorithms to make sure that they're not biased, right? Because these algorithms are going to learn in the context of the data they have access to, right? And so if that data is biased, for instance, maybe you only get the kind of data that could be easily fed into these algorithms from certain hospitals, which are in certain parts of the world, right? Which are seeing patients of particular genotypes, right? That the outcomes you get may be biased towards that training set, right? So, you know, we need to I think we need to think a lot about robustness, flexibility, generalizability of these approaches, but they have huge potential.